Our fourth and final speaker today is going to be Dr. Brett Ramirez. Dr. Ramirez is an associate professor in agricultural and biosystems engineering at Iowa State University. He leads an integrated research and extension program focused on ventilation design and management, climate physiology, mass mortality management, and several other topics related to swine facilities. His mission is to provide and advance the science and technology needed to address the aforementioned areas in swine production systems. His program aims to generate practical solutions to current and emerging issues surrounding animal agriculture and its producers. Please help me in welcoming Dr. Ramirez.
Am I good to walk anywhere? Oh, okay, cool, awesome. Thank you very much for the introduction, and thank you all 20 of you for staying till the very end. When I saw the mass exodus of people leaving. Yeah, right, you talk about ventilation, everybody's like, nope. So no, really, thank you for staying to the last but not least presentation. So today I'm going to talk about, I think down here might be better because I'm going to trip down those stairs if I'm not careful. We're going to talk about barn filtration challenges and opportunities for both negative and positive pressure filtered sow farms. And no, I do not have the theme song with Queen and David Bowie to play with the title, but I did try to keep at least one thing with the theme. So kind of some of the things I'm going to cover today are going to be related to design. You know, have we got it figured out? Is there a optimal design? Is there a best design? Is there one that's out there that is vastly better than everybody else? Wind effects, I think this is one that we struggle with on both types of farms because I think they're equally have their challenges associated with wind affecting those farms on whether it's the exhaust shutter or on the intake side. Either way, wind is going to have an effect on those barns. Environment, are we getting the best environment inside those farms for those pigs? I mean, I think I see a lot of times, especially negative pressure barns tend to be a little bit more choked. They tend to not really get that ventilation rate probably as high as we would like. I think positive pressure probably is up in the right ventilation rate. It maybe comes down to more of a distribution and actually getting that air distributed throughout those barns, even though I think we do have enough ventilation. It's just getting it into the spots that we need it. Control, I probably won't touch on this much, but I do think we're still back and forth on different control logics and what are the best ways to achieve that. And then collaboration, you know, sharing knowledge and, you know, getting the great minds together to really kind of figure this out and get enough information so we can, you know, get that design back to the top and start figuring these things out. So I did want to show kind of a map of all the sites in Iowa. As you can see, there's a lot of black globs. Those are all hog farms. So you can see if you have sow farms located in these areas, I'm sure you can visualize them because this laser does not work on the screen, which also that screen is extremely hot, by the way. I wish I had a thermal gun to gun it, but it is toasty up there. Should have brought one from the 4-H thing we did this morning. So high disease pressure, filtration is generally a pretty good option in these areas because there's just a lot of pathogen in the air. Didn't want to bring out, and I think the talk before me was perfect to set this up on filtration. That last little line down there at the bottom, you know, filtration really only works if we don't drag it in, right? And so I think following those ABCs is a great thing. You have to have that done first, then comes filtration. If you can't do those ABCs right, I'm not sure if filtering is really the best option because filtration costs a lot of money to do and a lot of money to keep doing, and it's hard to keep it going right. So I think get the ABCs, that was perfect talk to go before, so keep that in mind. So things when, you know, thinking about filtration and other factors, you know, these are just some common ones. Location, you know, are you in the middle of nowhere, South Dakota versus in Hardin County? You know, two totally different locations and they have two totally different disease pressures. Climate, you know, when designing these systems, I think climate plays an important role because in different climates require different ventilation rates, different cooling systems, different things to think about. Cost, you know, is it worth it? Longevity, when am I going to have to remodel this and how maybe am I located somewhere where I'm going to have to change filters more frequently? Probably isn't going to need to go into it. Pig needs, what type of pig is it? What do I need to provide for it? Management, you know, does it fit within our existing management structure? What is all going to have to change when we go to filtration, right? When Filtered sow farms are a lot more difficult to navigate when you're inside them and moving about. Like, they're not as easy. You can't do certain things that you could just do at a finisher. Control, what kind of control logic am I going to use to do this? And then generally, the whole overall ventilation system is important to keep in mind, because these systems are far more complicated than a standard run-of-the-mill finisher. There's so many more moving parts, so many more things that all have to work together for that system to truly be effective and achieve the results that we're looking for. So then diving down more into the ventilation side of things, air distribution patterns, where do I put my inlets? How do I get that distribution? And especially when you get to a lot of these larger farms, it's hard to get air all the way across a 100 some odd foot wide by 400 or 500 foot long barn. That's just a lot of volume of air to get it distributed evenly. Fans, we'll talk more on fans, but what kind of fan am I going to use? Probably wouldn't want to use a belt-driven fan in some of these systems, because there is just a heck of a lot of pressure that those fans are going to have to overcome. There's some good ones, but those belt-driven fans don't hold up as well as some of the kind of newer direct drive fans. Making sure we get the correct animal exchange rate. If it's on a negative pressure filtered farm, do we have enough soffit opening to get that air up into the attic so it can go through those filter boxes? What do we do about pit transitions and annexes? Do we vent those? Do we just cover them up? How do we manage that within the whole system? Right? If it's on a negative pressure farm, obviously we probably don't want those, because they're going to become inlets. Then it's going to get sucked in. Fan staging, if it's on however we want to do it, got to keep that in mind. Are we getting the transition between min and max correctly? Supplemental cooling, most likely probably just going to use evaporative cooling pad, so that one's actually relatively simple. Switching over to positive pressure is a whole different line of thinking than negative pressure. You actually have to actually bend. The more and more I think about positive pressure, the more and more it makes my head hurt and how much I don't understand it sometimes, even though I feel like I've got a good grasp on things. But when you switch to positive pressure, you do have to switch how you think about things, because it is not a traditional negative pressure system. Types of ventilation systems, facilities, filtration. Another one would be, I should probably put up there, infiltration. So obviously on a negative pressure farm, it leaks inward. So get your spray foam out, because that's what it's going to take, or grease gun, because you're going to have to seal that barn up to the best of your abilities, and it's still probably not going to be perfect, but it might not need to be perfect. Same is said on positive. I think we sometimes overlook the needs for reducing infiltration on positive pressure barns, because we got to keep the pressure in, because if it's going to leak out, guess where that air doesn't go? To the pigs, right? So if it's blowing out through your attic, you're losing pressure and airflow that should be getting down to where the pigs are at. Or if you're losing it through the room, then you're losing control of where that air is actually going to exit those barns. Filter selections, everybody has their preference and what kind of pressure you're at in that area. So just brief overview on negative pressure. I'm sure most people are familiar, but if you're not, negative pressure is kind of what it is. It's basically take a traditional system and add filters to it where it makes sense. So sometimes in just this, I gotta stop pointing at this thing knowing it doesn't work. Visualize where I'm talking. Follow the red arrows. So you bring in air in through a evaporative cool pad, goes up into the attic. There's filters mounted on the tops of the inlets. It then goes through the inlets, and exhaust fans are going to pull the air through the system. What I don't have drawn on here, and which I should, is I should either have like a double shutter on it, so a lot of farms will have two shutters for backdraft prevention, and then I should throw kind of a weird squiggle for a sock on them too, just to add some fun. You can also tunnel these by, instead of bringing air up into the attic, you could also just take out that end wall and put filter walls, usually in a zigzag pattern, to increase the amount of surface area to accommodate those filters. So what that looks like up in an attic, traditional filter boxes. A lot of times these things have to be spray foam, because again, under negative pressure, air comes in, and so we want to make sure all that air goes through those filters. For more of a tunnel barn, or it also could go up into the attic. Here's an example of air on front side of the filters. On the back side, again, all spray foamed. Again, minimize infiltration is the most critical part. So backdrafting of unused fans is critical. Shutters leak, they leak really bad. So if that fan is off, it is most likely going to be leaking, and if it is leaking in, and that air is not filtered, it is dirty air coming in. So there's a lot of different ways to do backdraft protection. Usually, most common I see is a double shutter wall and socks. As much as I don't like putting socks on fans because it reduces that fan's output even more than it's already being choked. But socks are usually a good way, but those socks have to be maintained. A lot of times they're all over the place or got holes or don't seal up. So switching over to positive pressure, which gained popularity here in the late 2010s. So to think of this, it's the opposite of negative. So now we are going to be pushing air inside the barn and having it exfiltrate or leak out. So the benefit here is that that air is going to leak out of the barn rather than any of those cracks and gaps and joints where we can't seal the barn up. That air is going to leak out and not pull dirty air in. So oftentimes here we'll bring air through an evaporative pad. It's going to go through the filters. Then the fans are going to push air into the attic, which is then going to push it through the inlets, and then it's going to exhaust out through a controllable opening in the room, usually distributed along the lengths of the room to kind of help even out where that air, all that air is going to get distributed. So if you're paying attention, you'd realize there is a negative pressure in here, right, between the filters and the fan, and so that area has to be sealed extremely tightly because that is a possible vulnerable spot where you could get air to be sucked in, and usually those rooms are pretty much coated in spray foam to help mitigate that. So there's a lot of different designs. Thankfully, AP and Munners are in the room, so I got lucky on that one. So these are just two typical designs. I'm not as good as Suzanne and don't have my disclaimer up there. It was on the first slide if everybody was reading, so no hard feelings to whoever's design I'm missing. Different ways to do it. So there's a lot, you can, pads versus pads in front of filters, filters behind pads. I know there's pros and cons with each of them. Different ways to go between, using sealing inlets versus tunnel. Just a variety of ways to do it. Again, there's some pros and cons with each of them. So what this looks like in practice, again, here's an example where the pads are in front of the filters, also kind of configured in a zigzag formation, again, to just be able to accommodate more filters in that linear space going along the barn. You see oftentimes double stack cool cells, again, just to need more wall space to accommodate the large amounts of air that are going to go through those barns. And you're looking at the pre-filters on the side and a lot of spray foam, again, to minimize any of the air coming in between those cracks and all those joints that construct that filter wall. So again, example on some windbreaks. These are just two different styles that I've seen. There's a lot, when I get into the wind stuff, I'll talk a little bit more about this, but different ways because, again, if you've been outside in wind, what does wind do? It exerts pressure. As it exerts pressure, it is going to try to go into an open space. So a lot of times these windbreaks are used to help deflect that wind from directly colliding with those exhaust openings and creating a potential biosecurity risk. So a lot of times with these barns, obviously in positive pressure, the pressure part is important, and maintaining that positive pressure is important, so we must monitor it. So a lot of times if I'm working with a lot of people, I'll ask them, have you ever seen a manometer before? Most of them say no, and then you go step on foot of positive pressure south barn, and that's all you see. They're everywhere. It's like they disappeared for 20 some odd years and then magically reappeared, but except for they're about 3 times more expensive than they used to be. They're almost about $100 now, I think. But you have to monitor pressure and you have to watch it because you've got to maintain that positive pressure to keep that air leaking outward. So just examples of kind of what it looks like. It's all through the sealing inlets and backside of some of the filter walls. So you can see in this one with the fans in the upper right, that room is spray foamed, again, to help keep that negative pressure chamber as leak-free as possible. So static pressure and airflow resistance, probably a review, but as static pressure increases, the airflow from the fan decreases. And so we really have to keep this in mind with adding filters, because all we do with these barns is we add resistance, which decreases the amount of airflow those fans move. So I think in positive pressure somewhere, I think those fans are going to work against about a 0.05 to a 0.3. Negative pressure probably maybe around a 0.2 to a 0.25, and actually I think that one might even be higher as you start adding double shutters and socks, and that even I could see that one being much higher than that when you start actually adding all those things up. Example of too high static pressure, if that door slams shut and almost takes your fingers off, that is probably a good indicator that that barn is choked for air and something needs to be opened up, whether it's in the soffit, inlets, exhaust somewhere, that barn needs to open up. So remembering that static pressure is additive is critical, making sure that we actually account for all these pieces in the system that all have to add together. So these are just two diagrams we made that show all these different pressure losses and how they interact with the system from outside all the way back to outside as it goes through the pads, the filters, the inlets, through the fans, and then through whatever else is in that system. And all these losses all have to be summed together to find a potential operating point that we feel comfortable with when trying to pick which fans we're going to use and at what pressure and air and subsequent airflow to get up to the ventilation rate that we are trying to achieve. So you see with negative pressure with the fans there, or positive pressure with the fans typically pad and filter before inlets and exhaust, versus negative pressure adds all the way up before it gets to the fan where it's the last point in the system. So again, looking at this is an example of initial resistance versus filter face velocity. Again, we typically go to the low end because we are trying to minimize the static pressure loss across these filters. It's sometimes some of those with inexperience might try to do these if they were in an HVAC system up in the 500 to 600 feet per minute range, and that is an absolute disaster if you're using axial driven fans like we do in agriculture. So we got to typically go on the low side, trying to really balance our static pressure loss through those filters with really the number of filters we really want to buy. So it's kind of a balance in where it works for your system. So typically we're down in the 2 to 175 range, and again trying to keep that less than about a 0.15. Sealing inlets are always going to be somewhere between about 0.06 to a 0.08. Can't get rid of those in positive pressure because that's where the air is going to have to go through, and if you're going to have a velocity through those inlets to make sure that air actually gets into the barn and starts to mix. Evaporative cool cell, the more I look at these, the more I think it's important to pay attention to different manufacturers and understand what the static pressure loss is and what base velocity that you want to size at. They all tend to be a little bit different. This is the example of the one I pulled, showing that at about 3, just shy of 400, they're at about a 0.05 and a saturation efficiency around 70%. Sometimes some farms tend to go a little bit higher, knowing if they have filters, evaporative pads are a little bit cheaper, and if you want to decrease a couple 0.01s off that total static pressure, increasing that evaporative pad area is a good way to do it, just so you reduce the amount of restriction on that system. Airflow ratio, not one we use commonly. Oh, come on. What did I do? Sorry. Anybody know the airflow ratio equation off the top of their head? It was just up there for a split second. So airflow ratio is the ratio of the fan airflow at a 0.2 inches of water column to 0.05. And so what that tells us is really how stable that fan curve is. So what we're looking for is a stable fan curve, because when we start to add resistance and then also as barns age, and that static pressure kind of increases over time as it does, we would like a nice stable, pressure stable fan that has a high airflow ratio. I usually like to be above about a 0.82, 0.8, just because I know then at least as things start to build up and get dirty, that fan's still going to keep its output at a relatively high rate and not really fall off, which you'd see with an airflow ratio below about a 0.7. Those fans are going to drop off pretty good. So these are two examples of some fans showing the difference between the one on the left's a 0.55 versus a 0.84, and the other one's a 0.84 versus 0.67. So then if you do some math on 1,013 fans, if you have fan at A at 0.15, and then over time it starts creeping up, you'll lose about 100 CFM per sow, just as that if you go from a 0.15 to a 0.3, which is, it's quite a bit over all those fans, keeping that in mind. So as we start to talk about static pressure, and this is leading into my wind discussion. So here's an example that was sent to me showing the static pressure. And if you look at the dates, this was last weekend. So what was it outside on Saturday and Sunday around here in central Iowa? It was hot, humid, and windy. So This barn was obviously at max vent because it was in the mid to high 90s. So obviously this is not the ventilation changing. This is purely maxed out. That is purely the effective wind on that attic. And you can see that's over the course of only, was that about an hour on the left. And then if you're paying attention to the screen on the right, that's the real time that was recorded. And you can see really how much that fluctuates in that short of amount of time. And so this is what just wreaks havoc on all of our systems, is Mother Nature and the wind. So for me, this is where it gets really hard to potentially control off something like this if it's that dynamic. At what point, even with the averaging, how do you make decisions on something that changes that frequently and that can never stay that stable, across just, and I'd say it was a little extreme this weekend just with gusts up into about the 40, 45 mile an hour range, but that's not completely uncommon. So looking at wind speeds over the last, is that about 4 years? So chart on the right shows wind speed from 22, 23, 24, and 25. So we're off to a great start here in 25 with wind. Definitely maybe not trending in the windier direction, but there is definitely some more wind. So the wind rows on the right is from 2005 to 2025. You can see when I made my slides because the date's right there. It was not the day before, it was actually a couple weeks. What I want to show there is that the wind is easily in that 10 plus, 15 to 20 plus range. And more importantly, which direction is it coming from over that, was that 20-year period? All of them, right? There is no direction that's safe from the wind. And it looks even better when we dig into the, so last summer and then this winter on the right. So prevailing winds in winter, typically out of that north-northwest, but what about all those other periods, right? It's surrounding the farm. Again, on summer, usually out of the southeast, but again, it's coming from every direction. So I think when we get talking to windbreaks and windbreak strategies, you have to be prepared for all wind, right? We can't just target seasonal winds because we're slowly losing seasonal winds and they're just becoming wind from every direction that we have to keep in mind when we're trying to evaluate strategies and not just say, well, look, the wind's usually out of the southeast in the summer, so let's make sure it works for that solution. I don't think we can do that anymore based on just how much this wind is changing. So we're doing a study on windbreaks. I do have a survey out on this, and if you would like to take it, shoot me an email. My email's on the last slide. Some of you I know in here already have. But we're trying to figure out a survey of all the different types. We're going to try and use that to create different small-scale models, test them in a wind tunnel, then throw them into computational fluid dynamics, and then generate best practices that hopefully improve windbreaks across the industry. So that's our goal from that.
Quick question.
Go for it, Mark.
Is that windbreak potentially close enough to compound our issue when our winds are the opposite direction?
On a sow farm or natural finisher?
I think more almost as a finisher.
I'm not sure if that would really have that much of an impact on that. Yeah. Might clarify this in a second. So all these different windbreaks, that's why we're after them. So that's why we want to understand them better, just because I've seen a lot of different things tried and got to find a good solution for everyone. So speaking of wind, so I snagged these pictures. I wish I could claim them because they do a great job at showing windward and leeward pressures on buildings. They show how that wind exerts pressure on one side and then how it creates a positive and then also a suction on the other sides, and how when it moves around these buildings, it's quite dynamic, and there's a lot to consider in this, and it's not as straightforward as it may seem, especially when you get it coming at different angles. Right? These are very easy winds that you could easily predict what's going to happen from that wind, and then showing what it happens down there in the bottom right on, if you have an opening, how it creates that positive internal pressure, versus then on the backside it creates a suction. So again, depending on which way the wind comes from, it's either going to create a positive pressure or a suction, and then just think about the season. So now, where we had a positive pressure, it becomes a suction and vice versa. So it's always changing, and then I don't have one where the wind's running parallel to the barn, and the impact it has on how that pressure works with how we do positive pressure. So here's an example of a windbreak. The most effective thing you could have done was plant trees 30 years ago, because when you knew disease pressure was going to be strong and we'd all have to start filtering, but usually, unfortunately, nobody's got a crystal ball. So trees do a great job at blocking that wind way out and then slowing down by the time it gets to that building to actually really effectively reduce that wind. Right? Especially trees would have been great when barns were curtain sided, because you would have wanted them all tall and then you wouldn't have any wind going through the barn. So, but I think tree with that higher, taller out does probably the most effective job at actually reducing that localized wind at those barns, but that's not very achievable, right? We can't go figure out how to get 30, 40-foot trees around our farms. So another one, I just pulled these offline. I can't claim the knowledge on these, but I think they're interesting to look at and how people have explored these things differently. Using a solid wall, which I'd say most farms have a solid wall as their windbreaks. How it creates that high turbulence zone, because that wind has to effectively compress as it goes over, and then conservation of mass, it creates it all has to come back together, and it forms that turbulence zone behind there. And then your shelter is really actually farther along, but oftentimes it's either going to hit a wall or a roof. So then what they show with like a porous one down here, which I thought was kind of interesting, of really just trying to decrease that wind and then slow it down, but then you don't create as much turbulence because you're still letting some of that massive air through that windbreak, and letting it kind of reconverge rather than having it crash and try to figure out how it can get back together. So environment. So we'll talk a little bit about cold weather and a little bit about hot weather. So oftentimes, so particularly for sow farms and also for finishers, we design inlets off max ventilation. Right? We have to make sure we have enough inlet capacity for how much is going to go through the attic, whether it's a finisher or a positive pressure sow farm. So we typically end up with about 3 times as inlets as we need. So when you have that many, it's going to make the cold weather side a little bit tricky because we don't need all those inlets. We also then don't have infinite amount of ceiling space, and we have to put them in rows. So they end up getting really close together when ideally we probably would like them spaced out more, but that's just, it's not possible when you have to fit that many inlets on that ceiling. So that becomes really important to make sure we're verifying our inlet air speeds, and then if we end up closing some or using only one side, it becomes even more important that we get up there with the kestrel, make sure we're getting that 800 to 1,000 feet per minute, making sure we're getting that good distribution, because some of the positive pressure barns do get hard to ventilate in winter just because of how many inlets there are and how much airspace that has to get air to move throughout across rooms in both directions before it gets its way out through the exhaust. And I recommend, if you can, use a spreadsheet, do some math, get things set up, get a program, get something that you can reference so you can keep doing the same thing and improve it over time. So changing inlet and exhaust openings on part of the room will affect the airspeed across all the inlets. Right? So this all acts as kind of one big system. As you make changes in one spot, it has impacts in other spots. So we have to keep in mind that as we do this, that it can't only just focus on one part, because there's a subsequent effect down over there. So it does, even though we like to think of them as zones, and we typically do zone them, we do have to kind of keep in mind that it's all going to have impacts, throughout that whole space. We also have to remember that these relationships are not exactly linear, and that they are all going to kind of do some funny things as we start to mess with things. So constant fan speed, if you close inlets, it increases airspeed. You open inlets, it decreases airspeed. Generally, that makes sense and holds true. And then as we keep our inlet opening constant, you increase fan speed. Sometimes the airspeed increases. Sometimes you got to factor in what does the static pressure do to that fan. Maybe the fan speed also slows down. So there becomes it's a very interconnected system, and we have to pay attention to, when we make all these changes, that there's going to be different impacts on the system. Hot weather, I'd say these are probably the 5 hot spots that I often run into. Most of the times if I'm dealing with this, the dead sows are in the middle of the barn. I've seen it very hard to get air there. It's in the middle. It's usually 250 foot in either direction from the nearest fan, and it's just a long way for them to then get it out through the exhaust. I also see some issues in corners. I've noticed a lot start adding little small exhaust openings in corners just to help get just a little bit of air out through those corners, because it tends to just create these dead spots because there's no real easy path for that air to make the correct turns, and it doesn't really want to flow into a corner when the exhaust is 25 feet to the other side of where that corner's at. So oftentimes I end up using stir fans just to help mix, or if it's in hot weather, just to help provide some airspeed and cooling over those sows in the middle of the barn. All right, so now we're going to talk about humidity, and unfortunately it started raining because I'm not going to ask you what the humidity is outside, because hopefully there's only one answer, which is 100%, because it's raining. Usually I like it when it's about 92 degrees outside and real muggy. I like to ask the question, and then everybody says 80, 90, 100 because it's so miserable. Most likely it's probably about 65, 60. So what I did was, I've been on this, and I'm big into when cool cells are supposed to turn on. I've been thinking about it for a long time now. So this is for Algona, June to September of last year, when it was over 66 outside. So there's this rule called the 80-80 rule. If it's above 80 degrees outside, it's below 80% RH outside. And so held true for 98% of the time. So that worked out. I mean, 98 is close to 100 for me. So that holds pretty true. So if it's over 80 degrees Fahrenheit outside, it is less than 80% RH. So then what got more interesting is when I dug into this a little bit more. So when it was below 80 and below 80%, it was actually about 38% of the time, which kind of surprised me. That's pretty dry, actually, and probably pleasant, shockingly, that we actually have pleasant weather here. And then below 80 and above 80%, 48% of the time, makes sense because that's generally what happens. It is just humid. So when do we get the conditions of below 80 and above 80%? When does that occur? Happens every day. Between what time period? Nighttime, right? So at night, we drop below 80, typically, and our humidity goes above 80%. Probably not to wait till the weather gets more consistent, and then you can check this. Just watch it. Today's a horrible day. Then there's another weird one, above 80 and below 80%, 11%, which makes sense. It never feels that dry here. We're not Arizona, unfortunately, but we don't get that condition most often. So what my point is that, yeah, see, I even had the answer on the slide. My point is that running cool cells in the middle of the night or too early in the morning is somewhat ineffective, because we are most likely over 80% RH, and you can't really evaporate water when the RH is over 80%, right? Cool cells are relatively ineffective. You might get 1 degree of cooling if you're lucky, but otherwise, if you know those pads are on early morning and it's still maybe 76 outside, pads are probably not going to be doing much, and you're probably just adding moisture to the barn and wondering why the barn's still warming up. But my pads are on. What's happening? Well, it's still really humid outside before it hits 10 a.m. or so. So future considerations, I'm almost right on time. Need to be thinking about barns in the future, having the right systems, trying to future-proof this stuff, making sure we're thinking ahead. If sows and genetics keeps getting better, nutrition gets better, do we have enough ventilation capacity for the future pigs? Do we need to update standards, do more modeling, figure out ways how to make these barns better? So that I'm going to leave on this one, because I've been in a lot of barns and I keep seeing the same thing over and over, and it's driving me nuts, because there's only so much I can do. I'm unfortunately not a skilled electrician or a maintenance person. I cannot fix things on the farm. I can't fix actuators or whatever it is, whatever is not working. So when I'm out there trying to optimize things, I'd really like to actually do that instead of having to point out what's broken. So, technology doesn't really matter if stuff's broken, stuff doesn't work. If the human programmed the controller wrong, there's really not much you can do in terms of trying to make that environment better. So I really hope for keeping on top of maintenance, getting it scheduled, getting it taken care of on time, just making sure that stuff works, because we can't really move forward if we're still 3 steps back on trying to get something fixed that has been broken for 4 years, right? When was the last time you've checked that all your fans work, or had somebody there that was knowledgeable to know if the fans don't work that they probably need to get fixed? So the other day I flipped on a bunch of switches on a farm. Guess what? 1 or 2 of the fans didn't work. It was just 96 degrees and they were short 2 48-inch fans out of 14. Maybe not the end of the world, but it still matters. So That's my last one is, make sure things works and give you a chance for good success in the future. So thank you, and thank you for hanging out till 4:25.
So comparing the negative versus positive systems, one thing you didn't mention was the challenge of having more moist air inside being forced in through the walls and condensing and causing issues with that. I'm just curious, what are people talking about to try to reduce that effect?
That's a good question. I'm not sure if I really have heard too much about trying to minimize. I mean, every time I'm in there, there's enough spray foam on joints that maybe there's not as much, but I mean, barns still leak like a sieve.
I didn't know if people were going to the level of changing the building material to be less absorbent or have an issue with all that moisture. That's what some people talk about, is actually going and changing what material the wall is made out of.
And going to like SIP panels and steel construction. I mean, that's about the only new one I've seen. The rest of all the ones I'm on are all remodels. So they're, hasn't really changed too much of the.
That's one thing you wonder about. Hey, just put positive pressure to it, you got no worries, It's like, they're especially existing buildings, and now you're forcing all that moisture into the walls and stuff. How long it's gonna last?
So in the barns that you've been working with, do you use any sort of humidity sensors to control the panels, the cooling cells?
None that I know of do.
Is that worth doing or no?
I think it's worth considering. It's just there's a lot of challenges with using humidity sensors. You have to first believe that it's going to work forever or work long enough and stay within calibration. So I mean, if you're trying to say only turn the pads on when it's less than 70% outside, your humidity sensor is generally plus or minus 5% typically. So then does it get out of calibration? Do you really trust that humidity sensor enough to make that kind of critical decision? I'm kind of on the fence on that. I'd probably rather use weather data or something, or use temperature, and you follow the 80-80 rule, for example, and kind of stay with temperature, because temperature works pretty good. So.
When do you anticipate to have the results of the windbreak survey, and will that turn into an explicit definition of the most right answer?
As soon as I get more people to take the survey, and it probably won't have that, because we'll have great options that have pros and cons. Spoken like a true academic.